Ever wondered how a G-Node B decides how much power each UE gets? Downlink Power Control isn't random, it's a precise balance of beams, reference signals, and PDSCH power allocation. Let's uncover how 5G optimizes every transmitted bit.
Welcome back to 5G RF Features Explained. Last time, we looked at how your phone, the UE, adjusts its power to stay connected and then avoid interference. But what about the network side? In this mini episode, we are flipping the script and exploring downlink power control, how the G-Node B shapes coverage, steers beams, and boosts performance across the entire cell. Unlike uplink, where every UE power is actively managed, downlink power control is centralized. All transmission originates from the G-Node B. Its goal: deliver sufficient signal strength across all users while avoiding excessive interference to neighboring cells. In 5G new radio, downlink power isn't an instant feedback controlled process like uplink. Instead, it's governed by RRC configured parameters and scheduler decisions. The main factor includes total cell transmit power, for example 49 dBn per carrier, power allocation per resource block, per antenna port scaling, beamforming gain, and pre-code weights. Beamforming dramatically changes how downlink power is used. Instead of spreading energy uniformly across the cell, the G-Node B concentrates power directionally toward UEs or groups. This allows higher SINR for the same total power, improving throughput and coverage. However, when multiple beams are active, the total power must be shared among them. PGPP defines several RIC level parameters controlling downlink power distribution, such as PDSCH, configure common power control offset, PBCH block, and CSI-RS transmit power, power allocation across MIMO layers. These parameters let network planners balance coverage, reference signal quality, and MIMO efficiency. In advanced deployments, power balancing happens across both microcell layers, which is for wide area coverage, and small cells or beams, which is for capacity hotspots. The G-Node B dynamically adjusts beam priorities. For example, lowering power for less loaded beams to reduce interference and then boost SINR on others. Downlink power directly affects CQI reports and thus MCS selection. A higher transmit power per beam improves CQI, enabling higher order modulation like 64 QAM or 256 QAM. The G-Node B scheduler considers both beam power and channel feedback to achieve optimal throughput per UE. There are some main challenges such as power sharing across multiple beams and carriers, limited total power from G-Node B output, neighbor cell interference and PCI coordination, energy efficiency versus coverage balance. Modern AI-based SON, the so-called self-organizing network tools, help optimize these trade-offs dynamically. Downlink power control is less about per UE feedback and more about intelligent power shaping across beams, carriers, and cells. It complements uplink control by defining how the network side manages its energy and spectral footprint. Next, we'll continue with episode 7, scheduling and HARQ, to see how time, frequency, and retransmissions work hand in hand with power and link adaptation. That's all for today. If you like this video, please subscribe, share, and like. Thank you.